My Govanen Haldir, you are most welcome. Due to overwhelming popular demand, this next tutorial shows how to create a simulation inspired by a popular children's toy. Well, popular with nerdy children like me. Not that I ever had the toy. We were poor when I was a child. Poor, I tell you. In this video, I will be doing a lot of rigging with just a soupçon of particle work thrown in. The particles are used to create the ink effect, so once created they just sit around doing nothing. Worst particles ever! So, how does it work? The movement of the pen looks quite complex. After all, if it was simple, the shapes would be boring and it wouldn't be a semi-popular children's toy. However, we can break down the motion into a series of simpler transformations. Looking closely, we can see that the pen is offset from the center of the slave gear, which in turn rotates about its center, and simultaneously it also orbits the main gear. We will have to be careful to match these two rotations, otherwise the gears will not mesh properly. Modo is good at managing this sort of hierarchy because we can construct stacks of transformations within an item without having to resort to nested stacks of locators, which would make the scene much more complicated. Here is a sneak peek of the rig that we're aiming for. The whole thing is quite flexible. We can control a number of teeth in each of the gears, and no matter how many teeth we have, everything still matches up as the slave gear rotates around the master gear. And finally, as the pièce de résistance, we can put the slave gear inside the master gear. And now we have a rig where the slave gear rotates around on the inside. We also have a control that allows us to position the whole rig however we like in our scene, and the controls go along for the ride. Well, it's the job that's never started as takes longest to finish, as my old gaffer used to say, so let's get busy. Rather obviously, we're going to use the Modo Procedural Gear as the basis for this project. So let's add one of those into the scene. As you can see, this doesn't look a lot like the gear we saw earlier, but the procedural gear is incredibly flexible with lots and lots of settings. We haven't really got time to explore all of those, so what I'm going to do is just enter the settings that I've used, but obviously you can use different settings if you want. Now this can be our main gear, and what I'm going to do is create an instance of this gear to be the slave gear. This saves us having to set up all the properties all over again. But first, let me show you something important about these gears. As I vary the number of teeth, you'll notice that the size of the gear goes up and down, rather obviously, and the position of all of the teeth changes. All of the teeth except one, and that's the tooth at the 12 o'clock position. Notice that that tooth stays put. It will make our lives much easier if we arrange for the gears to touch at this fixed point rather than at any other arbitrary point. Trust me, I'm a doctor. So let's create our instance for our slave gear. And while we're at it, we'll do the good old renaming so that we can tell what's what. So this will be main gear. And we'll create an instance to be the slave gear. Let's move the slave gear up. And if I show you what happens if I vary the number of teeth in the slave, you'll see that this is really no good for us because the teeth are jumping around all over the place. So what we need to do is flip this gear over so that the 12 o'clock point on this gear matches up to the 12 o'clock point on this gear, and we'll have half of our problem solved. Let's rotate this gear through 180 degrees to line up the 12 o'clock points. There we go. Now if I vary the number of teeth in this gear, the size of the gear is going to change, but these two are lined up properly. Well, not quite properly. There's a problem we've got to address, and that is that we don't want the teeth touching at teeth points. We want them to meet such that the tooth of one gear goes into the valley of another gear. What's the gap between teeth called? An interdental gap. So that's the next problem we have to solve. So what is the angle that we need to rotate the slave gear by in order to match the teeth up? Well, the angle between the teeth is going to be 360 degrees divided by the number of teeth. And we want to move by half that distance. So the amount we want to rotate the slave gear by is 180 degrees divided by the number of teeth. This will require some rigging. Let's bring the number of teeth of the slave gear into our schematic, and we want a math divide . 180 divided by the number of teeth is the angle that we want to rotate it by. And where are we going to plug this into? Well, we want to plug it into a transformation on the slave gear. So let's look at our slave gear channels. Now we've got a position. This is just me offsetting the gear from the center so that we can see what's going on. And we have this rotation, which was the rotation to line the 12 o'clock points up correctly. So let's rename this to be something so that we know what it is. Let's call this align stationary. Now we need another rotation on top of that in order to match the teeth up. So let's add in a new transformation, a rotation. Now the order of these transformations is important. As with most things in Modo, these transformations happen from the bottom up. So at the moment we're doing the rotation to line the teeth up, and then we're moving the gear up into place, more or less. If we were to apply this rotation after that movement, we won't get the effect that we're looking for. And I'll show you that by changing one of these. Let's say we want to rotate it by 45 degrees. That is really not what we wanted. The problem is that we've moved up and then we rotated around the origin. We want to do the rotation before the movement. So let's put that back and move this rotation down below the position. I'll just point out that in these transformations there are handy little symbols here to indicate what kind of transformation they are. It took me ages to work this one out. There's a little rotation sign for rotation and a translation sign for translation. How hard can it be? Right, so what axis are we actually interested in rotating this about? I think we're interested in rotating about the axis into the screen, which should be the Z axis. So let's drag that rotation into the scene, and I think I'll split it off just for convenience. And we've rotated by 180 divided by the number of teeth. If we zoom in, we can see that the teeth are now properly aligned. And if we change the number of teeth, that alignment should be maintained. Well, let's give it a go. Number of teeth is going up and down, but we have a nice meshing between the two gears. Super. The next job is to work out the distance between the two gears. Well, roughly speaking, it's going to be the sum of the radii of the two gears. So we go from the center of one gear by one radius, and then from that point to the center of the other gear by its radius. There's going to have to be a slight adjustment because we don't want the gears sitting point to point, we want them meshed together, so we're going to have to reduce that sum by a small amount to get the teeth to mesh. So what is the correct formula for the radius of a gear? Well, we need to do a little bit of geometry to work that out, and this diagram should help. So for a gear with tooth spacing SP, the distance halfway between the teeth is going to be SP over 2. And the angle covered by that distance will be 180 degrees divided by the number of teeth, as we showed earlier. Now we can calculate the radius because sine of the angle is going to be equal to the opposite distance over the hypotenuse, which is the radius. So that gives us the formula that sine of the angle 180 over nt, the number of teeth, is equal to the tooth spacing divided by 2 times the radius. And we can rearrange that formula to give this result, that the radius is going to be equal to the tooth spacing divided by twice the sine of 180 over t. So we've got our formula. Now we need to convert that into a piece of Modo rigging. I'm going to create a new workspace just to keep things neat. And let's call that something sensible like gear radii. How many i's in radii? So what do we need to make up this formula? Well, looking at it, we need a sine function. We need a couple of divides. I'll use some that I prepared earlier. What else do we need? We need a multiply because we're going to multiply the sine by 2. Math multiply. That should be enough to be going on with. So let's work from the inside out. We need the argument of the sine function is 180 divided by the number of teeth. So let's put 180 in here. And we'll leave the number of teeth dangling because we're going to connect that up later on. Connect that to the input of the sine. The result of the sine needs to be multiplied by 2. And the whole thing is going to be at the bottom of another divide, and this divide is going to be the tooth spacing divided by the result of this sine calculation multiplied by 2. So this is our basic rig for that formula. Now we're going to need 2 copies of this, one for the first gear and one for the second gear. We could just copy these nodes and create another version of them, or if we're more intelligent, we could create an assembly and then create an instance of that assembly. Then if later on we discover we've made a mistake in the formula, we can edit just the one version and both of them should update automatically. So let's create ourselves a new assembly. Let's call it something sensible like gear radius. Here we have our new assembly. We want to put these nodes into that assembly. If we have a look at it, there's nothing in there at the moment. If we select those nodes and then we can right click and move nodes to our assembly gear radius, and then if we go in again, there we go, they're there. We now need to expose the inputs and give them sensible names, so let's do that by dragging this onto the input. Remember, this is the tooth spacing, so we'll call that tooth spacing, and this is the number of teeth. Let's rename that exposed channel to number of teeth. And we can expose the output, and result is as good a name as any, so we'll stick with that. And now we have a nice packaged assembly where the names tell us exactly what it's going to be doing for us. Okay, so let's give that a go. We want to feed in the tooth spacing and number of teeth from the main gear. So let's go and find those. Tooth spacing, number of teeth, and connect those up. And this distance here we can feed into the offset for the slave gear. So go back into our slave gear and find its translation component, pull the Y offset into the workspace, and this position should put us roughly at the circumference of the main gear, because we haven't yet calculated the radius for the slave gear. And lo and behold, it does. Let's just test that by adjusting the number of teeth on the main gear and see whether or not the slave gear follows us up and down. And it does. The miracle of maths. Right, well, we need to do that all over again for the slave gear and then add together the two radii. So what I'm going to do is create an instance of this assembly. So select the assembly and then create an instance. If we go into the assembly, we'll see that Modo has done something rather odd. What it's done is it's created copies of all of our internal nodes. And this is an option on the command that does the instancing, and we don't really want these, so we can delete them. Okay, now we need to wire things up. So we're looking at the radius of the slave gear, so let's drag the channels for the slave gear into the workspace and then wire everything up. The slave gear, we're interested in the tooth spacing and the number of teeth. And let's separate these channels off. Wire them up. That's going to give us the radius of the second gear, which we want to add to the radius of the first one. So let's add in a math add. And now, by another miracle of math, we have the two gears more or less in the right position. Let's adjust the tooth count on each of the gears just to see that everything is working. The first one and the second one. That looks as though everything is working to me. Now you'll have noticed the slight flaw in this. We need a little further adjustment to make the teeth fit together perfectly, and that's what we'll do next. I don't have a magic formula for adjusting the distance between the gears. The precise value will depend upon how you've set up the shape of the teeth. For my setup, I've found that the adjustment is roughly half of the tooth spacing. In fact, it's close enough that half is good enough for me. So what we need to do is bring these two gears closer together by half of the tooth spacing. So let's add in a math divide, and we're going to divide by 2, feed in the tooth spacing, and we need to subtract that from the sum of the two radii. So let's insert a subtract node into here, insert math, subtract, and there we have it. If we zoom in here, we can see that the teeth are close enough together but not quite touching, and that's good enough for me. I think if we zoom in here, they're getting perilously close, and when the gears rotate there will be a little bit of intersection, which you can adjust for if you're worried about, but at the distance we're going to be seeing these, it shouldn't matter. So that's that jobbed. Next up is getting the slave gear to rotate around the master gear. Thinking back to the beginning of this video, recall that the rotation of the slave gear around the main gear consists of two components: a rotation around the center of the main gear, and then the rotation of the slave gear itself in order to match the teeth together. So the first of those rotations is going to be relatively straightforward. Let's create ourselves a new workspace. Let's call this slave rotation, and we'll make it active. What we want to do is have the slave gear rotate around the main gear as time goes by. So let's rig in some time, and let's use the frame number in order to drive the angle for the rotation of the slave gear. So we need to scale the frame number by an appropriate amount. So let's add in a math multiply. And what shall we do? How many degrees do we want to rotate per frame? Let's start with 1. That's a good round number. And we want to feed this angle into a rotation applied to the slave gear. So let's look at the channels again. Now this time we want this rotation to be at the top of the stack, because the rotation is going to be applied after our positioning. So if you imagine that we start with the slave gear in the center, we do some jiggery-pokery to get it rotated appropriately to match the main gear, and then we move it up using the position transformation, and then finally we want to rotate it around the main gear. And the axis about which we're rotating again is the Z-axis. So let's add a rotation. It's in the right place for us. Let's drag the rotation into the scene and then apply that rotation to the slave gear. And now if I scrub the timeline, the gear should rotate around the main gear, and it does. So that was the easy part. The hard part is going to be to make sure that as the slave gear rotates around the main gear, it also rotates, and in doing so it matches the teeth up. So let's dive into that can of worms. So this is an example of where a bit of geometric intuition can take you a long way. So crucially, the rate of rotation of the slave gear is going to depend on the number of teeth in the master gear and the slave gear. And thinking about it, if there are more teeth on the master gear, then the slave gear is going to have to rotate more often. If there are more teeth on the slave gear, contrariwise, it's not going to have to rotate quite so quickly. So it sounds like that the rotation of the slave gear should be related to the ratio between the number of teeth in the master gear and the number of teeth in the slave gear. So that's enough words. Let's suck it and see. Let's add in a math divide node, and let's grab hold of the number of teeth in the two gears. And separate out the slave gear just to make it convenient. Number of teeth in the main gear divided by the number of teeth in the slave gear. will give us the ratio between the two, and we want to apply this ratio to the angle coming out from this calculation here. So let's add in a multiplication node, math multiply, and finally we need to apply this rotation to the slave gear itself. So let's look at the channels on the slave gear. We want yet another rotation in our stack, so let's add one in. Now this one wants to happen down below the positioning because we want it to happen before we move the gear up into this position here. Otherwise the rotation will be about the origin, and we want it to be about the center of the slave gear. So let's move it down a couple of times, and we want to adjust the rotation around the Z-axis. And if everything is as we hope, the teeth should now match up as we rotate the gear. And that, my friends, is a miracle. Let's just make sure this works properly. We want to adjust the number of teeth in the two gears and make sure that it works for all numbers of teeth. It's looking good. Slave gear. Well, I'll be jiggered. Well, this is pretty good going. We're nearly 30 minutes in and we haven't seen any particles yet. Let's remedy that now. Let's create ourselves a new workspace and call this Particles. And we're going to add in our particle system and position it on the slave gear. So let's add in a radial emitter, because that's a straightforward and simple animal. It's much too big for the scale of this model, so let's scale it right down. That seems good enough. And remember I said the particles weren't actually going to be going at any speed, so gets rid of any velocity, and we must remember to uncheck inherit velocity, otherwise the particles will pick up a velocity from the gear that they're attached to, and we don't want that. Select the particle systems and add them into the scene. And the next step is to position the radial emitter relative to the slave gear, and we can do that just by dragging it onto the slave gear and parenting it. And there we go, it's now attached to the slave gear. We don't want it in the center though, we want it offset a little bit, so let's change its offset. There, that will do. It doesn't really matter what it is. At the moment it's sitting in the middle of the gear, and we want to have the effect that the ink is being emitted by a pen that's sticking out of the bottom of the gear. So we want to position this at the other side of the gear. It doesn't really matter which side we choose. We can either just do it by eye and put in a constant amount, or we can do it properly and have the distance that it's offset by relate to the thickness of the gears. So let's go back to our main gear, and somewhere there's a thickness parameter. Let's drag that into our schematic, and we also want to have the Z offset of the radial emitter. Let's drag that in as well. And we don't want to offset by the entire thickness, we want to offset by the thickness over 2. So a math divide, or we could multiply by a half, much the same thing. Divide by 2, divide by 2, not 1, and stick that, and now it's perfectly aligned, and if we were to adjust the thickness of the gears, then everything would follow along nicely. Alright, I will show you. Let's adjust the thickness of the gear. There you go. Do you believe me now? Excellent. Right, well, this should actually do something useful now. If we run the simulation, we now see particles being emitted as the gear rotates. It's not actually rotating very quickly at the moment because remember we put in a fairly low number of degrees per frame. We can go back to our workspace and change that number. Let's say 2.5. And now we get a rather more rapid motion. Now it's just a matter of adjusting things so that we get the right number of particles. Let's bump up the emission rate. And we also want to run our simulations over a rather longer space of time. Right, let's adjust the number of teeth to something interesting. The complexity of the patterns that emerge from this mechanism is really related to the ratio of the number of teeth. So if there are lots of common factors between the number of teeth in the main gear and the slave gear, you'll get relatively simple patterns. If the two gears have no common factors, say if they're prime numbers for example, then you'll get a much more complicated pattern. So let's start off with something quite simple, and I'm going to put in 30 teeth in the main gear, and in the slave gear we'll have 20 teeth as it currently set at. And now if we run the simulation, we'll get a pattern that's relatively simple because there's a very clear relationship between the two numbers. They have common factors. But that's a nice pattern to be starting with, and you can fiddle around with these numbers to your heart's content. We need really to be able to visualize these things now, so let's attach something to our particles in order to see them. And I used a sprite. Now, sprite starts off much too big. Let's make it a bit smaller. Let's hit 0.2 millimeters, for example, and attach our particles to it and run the simulation. We probably don't need the full 900 for this one. Let's try 360. That's just a number plucked out of the air. It's done its business, and if we wind forward we can see the pattern build up over the course of 360 frames. So the last step is to turn these sprites into something that looks a bit like ink. So we'll need to attach a material to our sprite by creating an item mask, and let's set the material properties on that sprite. So we're looking at the material raise section, and I found that if you set the scattering amount to 0 and the absorption amount to 100%, that's a good setting for an ink-like effect. Remember, with the absorption color, the color of the sprite is going to be the inverse of the color that you set in here. So if I want the ink to be green, say, I will set the green to 0 and we should get green ink. Let's bring up our preview And at the moment we're not seeing anything. And that is because our sprites are incredibly small, and so their density is not high enough for us to be able to see the poor things. Let's go back to the sprite and find its density setting. It's only set to 1 at the moment. Let's wind this up to something ridiculously huge, 3000, and there you go, we can now see our ink. Now if we plop that on the top of a piece of paper, it's going to look a bit like ink. It's a little bit disjointed at the moment. We can fix that up by having more particles emitted, or by making the sprite slightly bigger. But in essence, that's job done. But before I go, I ought really just to show you how to set up some controls for this rig. Let's do the old trick. Let's start with a new workspace, and I'll call this control. I'll make it active. And the normal way to control things in Modo is to set up a locator and attach some user channels to it, and then wire those into your rig. And I'm not going to break with tradition, so let's add a locator into our scene, pull that into the workspace, and let's add some channels into this to control our rig. So under the user channels, we can add a user channel. Let's have main gear teeth, and that's going to be an integer. Default value, I don't know, 20. Let's use a minimum value, 10, maximum value, 50. It doesn't matter, whatever you want. Okay, and let's add in another one for the slave gear. Add user channel. I wish I could type. Slave gear teeth. Same settings. What else do we want to control? We might want to control, say, the thickness of the gears. Gear thickness. This will be a floating point value. And default value 0.002, that's 2 millimeters. Let's use a minimum 0.001, say 0.01. I don't know. It doesn't really matter. We can always go back and change these values by right-clicking on the channel and then saying Edit User Channel, and we can change all the settings that we selected. What else might we want to change? We might want to modify the speed at which the slave gear rotates around the main gear. Let's add another float channel in and call it rate or speed or whatever you want to call it. And we'll start with a default value of 1, and maybe we'll use this as a scale value, so from 0.1 to 5, for example. That gives us a range of scale factors on the speed. And then the final thing I'm going to add a control for is the offset for the radial emitter, i.e. where the pen tip is. That'll be the offset distance from the center of the slave gear. So add another user channel and say pen offset. It's going to be a float scalar, default value 0.002, say, for example. Start with a minimum value of 0 and go up to 0.01, say. Okay, so that's set up our channels, and then all we need to do is connect them to the appropriate parts of our rig. So for the main gear, we need to control the number of teeth. And the same for the slave gear. We also want to control the thickness of the two gears. We want to give them the same thickness, so let's pull thickness of both the gears in. For the speed, we're going to have to find the scale factor in our model somewhere. I think it was in slave rotation workspace, and it's this number here, this 2.5, which is the scale factor on the frame that says how many degrees per frame we want to rotate. So we're going to make this into a driven channel, give it our own scale factor. Let's put a copy of that node into our new control workspace and go back to the control workspace, and there it is, and we can put the speed in there. And then finally, the pen offset is going to control the distance of the radial emitter from the center of the slave gear. So the radial emitter here is currently offset a fixed amount, 4 millimeters from the center of the gear. Let's pull that in and make that into a parameter that we can control. Excellent, so those are all set up. And if we were interested in changing them, one way is to select the channels and then type C for the channel haul tool, and now we can interact with those things and make adjustments according to the values that we want. But we want to make the lives of the users of our rig as easy as possible. They won't know to go into this locator and select the channel haul tool. So rather than make them do all the hard work, let's make this locator something that they can see and something that looks like it's obviously something they should interact with. So let's change to a custom shape, and I'll stick with a box and solid. It's much too big at the moment, so let's change the size to 5 millimeters. There we go, that's about the right size. And let's move it out of the way so that it's not on top of the model. And then under the Assembly tab, we can attach a command to this locator. And the command that we're interested in is item.channelHaul. And now when users click on the locator, it will automatically bring up the channel haul tool and show the channels that we can edit. Let's show you that in action. There we go. All of our useful controls pop up. Job's a good one. So that's it for now. I'll include links to the LXO file for this project in the description below. Feel free to make use of it in your own projects. If you are new to the Modo particle system, do check out my earlier Modo particle videos here on YouTube. I have also produced some introductory training for the Foundry, which you can purchase from their website. I hope this video has been informative and, as always, thanks for watching.